long. And so we talked about general operators, we talked about the linear momentum operator, and now let's see here. I'm going to make sure I'm in the right position. Pun intended. Let's see. Aha, beautiful. Okay, so I'll remind you. Our potential energy operator, right? This is just kind of a reminder slide, okay? Our potential energy operator, we use this term V. And I've shown you in some cases we could use just a constant potential energy. As it turns out, a potential energy operator that we're going to see come back in Chapter 8 is the following: 1/2 kx squared, which is actually Hooke's law for spring constants. And as it turns out, this is a great potential energy operator to describe the vibrations of atoms. So if I have two masses on a spring, so recall there's force constant K. I know we're using the letters over and over again. So the force constant of the spring, or the spring constant, is K, and it is displaced over some distance x. So as it turns out, that 1/2 kx is a really nice potential energy operator to describe molecules and atoms. And we notice here in that operation, it still really is, there's no derivatives. It's granted it's not a constant because there's the x squared, but it's still just multiplication of this whole thing through. There's no derivative analysis, okay? What about the kinetic energy operator? Well, recall, I'm going to go back using this letter T because in some textbooks, the letter T is used for kinetic energy operator. And so recall, that was given as negative h bar squared divided by 2m. And remember, there's this second derivative function here, okay? And so now if I put these together, and I'm going to come back and talk about the second derivative in a moment, but if I put these both together to get total energy operator, that's where we use the Hamiltonian, okay, which would then be negative h bar squared 2m ddx squared plus 1/2 kx squared would become our total energy operator. When we operate that on a wave function, we need to get back an eigenvalue, a single valued constant. If we don't, then we have not used an appropriate wave function. Okay, so let's keep talking about this second derivative here, okay? So recall, the second derivative of a function is a measure of its curvature. So a large derivative indicates a sharply curved function. A sharply curved function is associated with a high kinetic energy, and one with a low curvature is associated with a low kinetic energy. So here is that kinetic energy operator. So here I wrote it as EK, but sometimes also T. I just want to get you all used to the various letters that are used in all the large number of texts on the subject. And so if we think about this, so this is kind of where we're also going to start to see some connection between this wave-particle duality, okay? So if we have this sharply curved function like this, okay, we see high curvature on this side, and we see high curvature on this side, all right? So there's a confluence. I'm going to draw arrows going either way, pointing, moving into that place, okay? And we note, of course, in the Born interpretation, we would say the most likely place is right here. And of course, there's no curvature at that point at all, right? At that top point, the slope is 0. Very interesting. We're going to come back to that. And then if we had this less steep function right here, okay, we can see there's lower curvature, lower kinetic energy than in this case, But all the same, we can still see that point there owing to a zero slope will have physical significance in wave-particle duality. Another way we can think of this, the second derivative analysis, if we look at a wave function, perhaps it looks something like this. Okay, so we can see as this oscillates and it gets to a higher and higher frequency, if we think about this kinetic energy going on, we have high kinetic energy on this side and low kinetic energy on this side, which would look something like this, right? So if my total energy is constant, then over to the right of this diagram, you can see there's a large kinetic energy and a small potential energy. But as we move to the left of this diagram and fixing the total energy, right, we could see the potential energy is in fact not constant through this diagram. Rather, it's changing. And so when we see something like this in our wave-particle duality, we would interpret this as a particle moving to the right. So in this reference frame right here, right, where let's say, this is my x-axis distance, this is 0, the origin. A wave function with curvature like this in our wave-particle duality would indicate, for one, a non-constant potential energy. And what that would actually give us, it would create a force on this particle, moving it in that direction indicated. Okay, very cool. So now